Good morning. Me and Ms. Bonita, we were tasked with looking at conic sections of rotated conics for the course analytic geometry and trigonometry too. So basically, in this presentation, we'll be looking at the general conic equations, XY terms rotation, rotated axis, simplifying equations, and identifying conic shapes.
All right, good morning. So basically what you're seeing on the screen here are a bunch of equations that we would have done in the last semester when we looked at conic sections. So these first two equations here, these are basically related to parabola, and these two here, they're related to the ellipse, and then these two here, those are related to the hyperbola. So, if we were to rearrange any one of these formula, it would give us this general equation of conic sections, which is ax squared plus cy squared plus dx plus ey plus f equals 0. So, for example, I'm going to rearrange one to show you how we get our general formula. So we have the formula y minus k squared equals 4p into x minus h. We know that basically what we're doing here is multiplying this bracket twice. So we're going to have y minus k y minus k. And this is equal to, if I am to use distributive law to simplify this part here, we'll have equal to 4 4px and 4p times minus h will give us minus 4ph. Over here now, simplifying this bracket, we know y minus y is y squared, y minus k, sorry, y times y is y squared, y times minus k will give us minus ky, minus k times y is minus ky as well. And minus k times minus k will have plus k squared. And of course, this is equal to 4px minus 4ph. What I want to do now is to put everything on one side of the equation. So basically what I'm going to have is the y squared minus k minus ky minus k. Oh, I should simplify this part first. So this minus ky is basically giving us minus 2ky. So instead of writing it twice, I'll just do the simplification one time. So we have minus 2ky plus k square. And now I'm bringing these two over here, over the equal sign. So this here is a positive 4px. It'll now be minus 4px. And the minus 4ph becomes plus 4ph. And that is now equal to 0. From here now, what I want to do is just do a little bit of rearranging to make it look like our formula. So we don't have any x squared term. So I'm just going to go straight to the y squared term. So we have a y squared. Then we have an x term, which is the minus 4px. And then we have our y term, which is minus 2ky. And then we have our constant f. So our constant f would be the minus, it would be what is left here. So we're going to have the k square plus k square and the plus 4ph equals 0. So in this equation here, this rearranged equation, we do not have an x term. So basically a is equal to 0. Our c term would be, c would be 1. The y squared term, there is a 1 here. And for d, d is equal to minus 4p. E would be minus 2k. And the constant would be, the f there would be k squared plus 4ph. And basically that is how we can rearrange the formulas to get our general equation. Also, point to note, those equations, the conics are not rotated as yet. Next slide, Sir Andrew. All right. So it says here, if a conic section is tilted so that its axes are not parallel to the x and y axis, then its equation will contain a cross product term bxy, and the equation will have the form ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. This is basically the general equation, but with an added term. And this here, for this equation, we will use this whenever we have a tilted or an axis that is rotated. So, yes, basically before the axes are rotated, they would be parallel to the x and y axis. But then after rotation, they're no longer parallel. So the equation will then contain the cross product, and we call it this term, the bxy term. Next slide. So, as an illustration, consider the ellipse with foci f1, 1 to 2, and f2, negative 1 to 2, and such that the sum of the distances from each point, P is xy on the ellipse to the foci is 6 units. So we basically have a graph or an ellipse, and then you have a point, the point P. And from there now we have two foci, and it's saying here that the distance from foci 1 to point P and the distance from foci 2 to point P, when we add those two distances, it's equal to 6 units. So this part of the equation is calculating for the distance from foci 1 to the point P. And then this part is calculating the distance from foci 2 to point P. And when we add these two distances, it's equal to 6. Simplifying this whole long equation, we're going to ultimately end up with 8x squared minus 4xy plus 5y squared is equal to 36. And from this here, relating back to our general equation, we can see that a would be equal to 8. The x squared term is 8. The b term is negative 4. Our c term is 5. The y squared term, the c is 5. And d and e would be 0 because we don't have the other terms there. And then f would be negative 36. Why negative 36 is because if we take this positive 36 over the equal sign for it to be a constant, it would change to negative. So we'll have negative 36 there. Next slide. This is the diagram that the question was talking about. So we have our two foci, foci 1 and foci 2. Now from foci 1 to point P, there would be a certain distance here. And then from foci 2 to point P, we'll also have another distance. And if we were to add these two distances, it would equal to 6. That is basically what the question was saying earlier. Next slide.
All right, so considering what we have done so far, we actually have, well, this part of it actually is the discriminant. And what this basically does, it works like a DNA test. Basically, it could tell us what the parent shape is using a specific formula. And that formula would be b squared subtract 4ac. And this would tell us, with rotation already being done, what our what our parent shape is. So there's a few rules that we need to remember, and that if b squared subtract 4ac is less than 0, it could either represent an ellipse, a circle, a point, or else has no graph. If it's more than 0, it could represent a hyperbola or a pair of intersecting lines. And if it's equal to 0, we could say that it represents a parabola, a line, or a pair of parallel lines, or else have no graphs. So if you see, we worked on, well, just now I'm working an example on it, but this is basically what it is. And we'll see how we use the discriminant to get our parent shape, or basically how do we know what shape the equation is talking about. So another one to remember is, what if we have a shape that is not rotated? Or let's say b is equal to 0. And since b is equal to 0, we would have this formula here to remember. Because this shape is not rotated, so it does not have a xy term. So with those two equations in mind, we move forward. And an example of this is, let's say we have 8x squared minus 3xy plus 5y squared subtract 7x plus 6 is equal to 0. And the question says, use the discriminant to identify the graph. So as I said earlier, we have to know certain things before we could identify the graph. And our discriminant being bx squared plus 4ac, minus 4ac. So first thing we gotta do is identify what is the term or our bx, or b squared, sorry. So our b squared is basically our xy term, which in this case is negative 3. We have to identify our a, which in this case is our x squared term, and it is 8. And we have to identify our c term, which is y squared, and that would be 5. And what we see happening is that when b squared subtract 4ac, or negative 3 squared subtract 485, we would get negative 151. And we would say that we know it could either be an ellipse or a circle. And in this case, it actually is an ellipse. But why can't it be a circle? And that is where these set of rules come into play. And that is because for it to be a circle, b has to be equal to, yes, as I was saying, for it to be a circle, b must be 0 and a must be equal to c. Because for a to be equal to c, it must be equally weighed. And the reason b must be 0 is because there cannot be an x term, or it would be a tilted shape. Meaning we would have, rather than it being a circle, it would be looking something like that. And we know that is an ellipse. Then we talked about degenerated conics. And degenerated conics, this is just a fancy way of saying it is a fail shape. Instead of having like a nice looking curve, it basically gives us a single point, a straight line, or two crossing lines. And it's like trying to draw a circle, but your pen ain't going the way it's supposed to. So rather than drawing a perfect circle, I get ending up with something looking like this, and we know that is not a circle. Miss Benita.
All right, yes. So, what we have here now is the xy coordinate system. So it says in figure 12.5.2a, the axis of an xy coordinate system have been rotated about the origin through an angle to produce a new x prime y prime coordinate system. And as shown in the figure, each point P in the plane has coordinates x prime y prime as well as coordinates xy. To see how the two are related, let r be the distance from the common origin to the point P and let alpha be the angle shown in the figure. Basically, so what we're seeing here is this faint line, the faint axis there, that is the conic before it is rotated. And then the other one is when it is tilted. The brighter line is when the conic is tilted a little at a certain angle. So, what we're doing is we're trying to derive some formulas here. If we are to look at the second diagram at the faint axis, we're going to see that first let's identify our points. They said to let r be the distance from the common origin to point P. So we know that our common origin would be here at 0, 0. And then we have our common point P. So the distance from the common origin to P, we're going to call that R. And then let alpha be the angle shown. So basically this alpha here is the angle between the tilted x-axis and the line that connects the origin to the point P. And this theta here is the angle between the tilted x-axis and the original x-axis. So, what we want to do is we're deriving a formula here for this part for x here. What took place here was they just formed a 90-degree from the point P to the original x-axis. And if we were to think back to CXC trig ratios, we would know that the cost ratio involves the adjacent and the hypotenuse. So considering this triangle, we have our hypotenuse being r, x would be the adjacent, and then we have our angle, which is alpha and theta. So what I'm doing here now is just making a formula with the information that we have. So x is equal to the hypotenuse, which is r, times the cos theta, or the angle there. So the angle would be not just alpha or theta alone, but the sum of both of them. So that is why we have theta plus alpha here. Yes, so that's our first equation. And the second one now, we'll be considering the other triangle. That is the tilted triangle. Again, they would have, excuse my lines, they would have formed a 90-degree from the point P to the new x-axis. And we can see here again that the hypotenuse again is r, but in this case we're using sine opposite and the hypotenuse because we're looking for this part here. Give me a moment, please. Yes. So we're considering our new triangle, and so what we're looking for here now is y. This y here. So again, I'm substituting using the information that is given to come up with my formula. We have the hypotenuse r, and then we have the angle again, theta and alpha. Next slide, Sir Andrew. These two formulas here, can you please go back to the previous slide? I would have said something wrong here with this one equation. This here is not for the tilted triangle, but it is for the original triangle. We're still considering this original triangle. However, we're using the sine ratio with the hypotenuse and the opposite. Next slide. So for these two equations, we're basically doing the same thing, but these two are for the tilted triangle or the rotated axis. This other part here, these were the trig identities that we would have done previously, and previously in the course, that is, not in the presentation. So how is it that we got our rotation equations? We are using these trig identities here and the information that is given to us. So, if we were to notice, I want to simplify these here further. So it said that the x prime is equal to r cos alpha. And by simply rearranging this, if we put the r here, we're going to have r cos alpha. And we know that r cos alpha is equal to x prime. So for this first equation here, the first rotation equation, we're basically substituting the r cos alpha with x prime. And, well, we have our cos theta here. We're bringing back the cos theta. And this other equation here, y prime is equal to r sine alpha. Again, the r, if we were to rearrange to put r here, we'll have the r sine alpha. And that there is basically y prime. So we substitute that there with y prime, and we have our sine theta. Same thing for this other equation. Y is equal to r sine theta cos alpha. Substituting the r cos alpha with the x prime, we're going to have x prime here, and the sine theta comes back, and the same thing with the latter part, the r sine theta is substituted with the y prime, and we'll have y prime here, and the cos theta comes back. So basically, the two equations, or our two rotation equations, are x is equal to x prime cos theta minus y prime sine theta, and y is equal to x prime sine theta plus y prime cos theta. Next slide. So Sir Andrew is going to show you some examples now with how we use them.
All right, so our first example, suppose the x-axis on an xy coordinate system are rotated through the angle of 45 degrees, theta equals 45 degrees to obtain x, x dash y dash coordinates. Find the equation of the curve. So first thing, let's check this out. What type of curve will it be? Will it be between like an ellipse? Will it be parabola, hyperbola, whatever? How do we know what it will be? So again, our DNA test comes into play. And as you remember, it is b squared minus 4ac, right? So we have b squared, which is, and this in this case, it's -1 squared. Subtract 4ac, we have 4, or a being 1, and our c being 1 again, right? Our a comes from x squared, and our c comes from y squared. And this equals to -5. So we know it is either an ellipse or a circle. Although it meets the requirements to, some of the requirements to be a circle, it is not a circle because b is not equal to 0. And for it to be a circle, b had to be equal to 0. So we know our shape is most likely an eclipse. But how do we have...
Andrew, please don't say eclipse.
Sorry.
It's an ellipse.
Ellipse. It mixed up in my head. Sorry about it. Ellipse. Yes. An ellipse. So how do we get it? And basically, we're substituting the values of sine theta in and cos theta in sine theta, which is equal to sine 45, and cos theta, which is equal to cos 45, into our equations, or the equations that Ms. Benita just looked at. And that is x is equal to x prime cos theta minus y sine theta, or basically we're looking at yes, what we're doing is that we're substituting into the rotation equations, right? So we basically put 45 here, 45 here, 45 here, 45 here. And we would see that when that is done, we would have gotten x is equal to x prime over root 2, subtract y prime over root 2, and y is equal to x prime over root 2 plus y prime over root 2. The next thing we would have gone and done is substitute into the given formula. And this part is basically we're taking these values. Yes, we're taking these values, the x value, or putting it into the equation wherever x is. And we're taking y, which is this, we're putting it wherever y is. And we basically do the plug and chug here. And it is a lot of working. But when put it into the formula, we would have gotten this up here is when it's being put into the formula. And when we start to simplify, we would have gotten this here. But this could be even simpler. And we would have taken our 2, bring it over, or to get rid of that 2, we multiply both sides by 2. And we basically eliminate the ones on top. So we have an x squared here, we have a minus x squared, so these cancel out each other. Negative x prime y prime, so these cancel out each other. We have, I don't think we have anything else cancel each other. So we have y to the third power and x, sorry, 3y to the second power and x to the second power is equal to 12. And we know that it's an eclipse, so we have to get it to equal to 1. So the way we do that is to put this over 12. So we put everything over 12, and when everything is being put over 12, we would have gotten this down here, or our equation for the curve, the curve graph. Right, so we see that how we moved from our equation of the curve that is given, the given equation to the equation of the curve or our ellipse. And this is how it would have looked. So it would have originally been on this axis, which is already rotated 45 degrees. And we would have found the original, which is on this axis here without the rotation. Our next example. So in our next example, we have, yes. So we have to find a new coordinates of the point 2, 3, rotated through an angle of theta is equal to 30 degrees. So the solution, we basically, x is equal to 2, we have y equal 4, we know cos is equal to cos 30, which is root 3 over 2, and sine is equal to sine 30, which is half. And again, we put it into our rotation equation, and we would have gotten our new x coordinates and our new y coordinates. All right, so that one was, well, basically very simple. But now we come to this equation here. And this equation could tell us what the rotation is in case we are not given the angle of rotation. So it has to be, but sorry. But it has to be that b is not equal to 0, because we know for us to have b here, it's a rotation. If we do not have a bxy term, it means that that angle, that shape has not been rotated. And that would mean that we would have this form here, where the shape has not been rotated. So example 3, identify and sketch the curve yx is equal to 1. So the first one, we know we do not have an a term. We have our yx equal 1. So in front of yx, we would have gotten 1. So b is equal to 1 and c is equal to 0. And we want to know what the rotation is. So we have cot 2 theta is equal to a minus c over b. A being 0 minus c being 0 over 1, which is 0. And we know this condition can be met because we would have gotten, yes, what was I? Yes. Tan inverse 1, 0. Tan 0, sorry. And we would have gotten 2 pi, which is 2 theta, which is equal to pi over 2, and theta over 4, because it's 2 theta, so theta, it would be pi over 4, which is 45 degrees. And we substitute cos theta is equal to cos 45, which is 1 over root 2, and sine theta, which is sine 45, which is, again, 1 over root 2 in the equations, or rotated equations. So we substitute into xy is equal to 1. And we would have seen that we would have gotten this equation here. And this is basically the equation of a hyperbola. Yes. So a few things more we want to do. Although we know this is a hyperbola, we need a few things before we could actually sketch it. And we would have gotten that a equal b equal root 2, with the exception that variables that are formula equation of a hyperbola. And to get our stuff, we use these formulas, which is x prime, y prime is equal to a comma 0, which is actually equal to root 2, 0. For the foci, we have c plus or minus c, 0, so we have plus or minus 2. And for asymptotes, we have y is equal to plus or minus b over ax, or we could say y is equal to plus or minus x prime. Using these, we would have seen that we have gotten our vertices, which is 1, 1, our foci, which is root 2, and again, our xy, which is negative 1, 1, and our foci, which is negative root 2, negative root 2. Using that, we would have sketched, so, yes. So having that, to obtain the xy equations of asymptote, it is desired that we use the form of before, and we substitute cos with cos 45, which again is 1 over root 2, and sine 45, which is 1 over root 2. So we would have gotten x prime, y prime, and we would have seen that x is equal to 0, y is equal to 0. So this curve xy is equal to 1 can be sketched. So there's also to look at, for theta, the values of sine theta and cos theta needed for rotation equations may obtain by first calculating cos 2 theta and then computing sine theta and cos theta from the identities. This basically means that sometimes we will be given some very ugly angles, and we could use these two here to help simplify, which we'll be looking at in the next example. But coming back to our sketch, our hyperbola would have looked, well, will look like this. So example 4, identify and sketch the curve. So first thing, we can identify the curve. So we have A is equal to 153, B is equal to negative 192, and C is equal to 97. We have cot 2 theta, which is A subtract sine A minus C over B, which is actually negative 56 over 192, which is equal to negative 7 over 24. And like I said, sometimes we would have some very ugly looking angles. So we would have used this instead, with cos 2 theta is equal to negative 7 over 25. And we split that into these two here. Cos is equal to the root of 1 plus cos 2 theta over 2. And that is actually equal to 1 minus 7 over 25 divided by 2, which gives us 3 over 5. Same thing for sine, and it would give us 4/5. We then substitute the values into our rotated equations again, and we would have gotten x is equal to 3/5 x prime minus 4/5 y prime, and y is equal to 4/5 x prime plus 3/5 y prime. We then again use the chug and plug, which basically we take the plug and chug, sorry. We take them, we input them into the formula wherever x is, we put our values, wherever y is, we put our values. And throughout this, you see they divide by 25 is because here we would have gotten over 5 and 4/5. So they basically they take the square and they factorize it outside. This could be basically simplified to 25x squared plus 225y squared minus 50x minus 200 is equal to 0. We divide by 25 throughout, and we would have gotten x squared plus 9y squared minus 2x prime minus 8 is equal to 0. And completing the squares, we would have gotten this here. And we know that this is an ellipse, so it would have been drawn like this diagram here. So a few things to remember: we would have gotten our general equation. We would have gotten our discriminant, which is b squared subtract 4ac. And we know this basically works like a DNA test for rotated conics. So if it is less than 0, it could be an ellipse or a circle. If it is more than 0, ellipse or circle. If it is more than 0, it could be a hyperbola. And if it is equal to 0, it is a parabola. We also have when the shape is not rotated. And for this, which I was supposed to mention earlier, is that if it is negative, it is an ellipse. If it is positive, it is a hyperbola. And if it is 0, it is a parabola, or if it's equal to 0. We also have our rotation equations. We have the equation to find find our rotation or the angle of our rotation. And we have this one down here for when the equation, the angles are not looking so nice, we use. And that basically brings us to the end of our presentation.
All right. Any comments from y'all?